Hi Year 12, hope everyone's okay. This video is the lesson on section 4.5 turning points. I plan on telling a more full story than what is presented in the book. I encourage you to watch this video and then look at what it says in the book. The very first thing I want to briefly mention is points of inflection. You don't need to know about these yet, but they aren't too hard and I just want to give you a brief description. A fuller explanation will be given in Year 13. After the brief description on points of inflection, we'll start the lesson on stationary points. You'll need some paper and a pen because you're going to need to make notes along the way. So feel free to pause and rewind as needed. Okay, so let's begin. So, as it says here, before we begin, because this isn't really the proper lesson yet, as I said, we need to know what a point of inflection is. So as I say, you don't need to know about points of inflection in Year 12. You'll meet them again in Year 13 properly. So the reason I want to briefly introduce them is to help tell the full story about stationary points. Now already I am encountering a little bit of technical difficulty. As soon as I've actually started the PowerPoint, it's frozen. And I'll be honest with you, I'm not planning on doing any editing, so this is just going to be one continuous video. So please feel free to pause it and take breaks and things like that because it could be quite long. So anyway, that's now recovered. So here we go. So what is a point of inflection? So this is the definition. Now, of course, this isn't going to mean a lot until I explain it in a bit more detail. But let me just state this definition and then give you a little bit of insight. So a point of inflection is a point on a curve where the curve goes from being concave up to being concave down. So what that means, we'll see in a second. So the curve could go from being concave up to being concave down, or it could go from being concave down to being concave up. So it's wherever there's a change of what's called concavity. So you're either going to go from being concave up to concave down, or you're going to go from being concave down to concave up. And there'll be maybe it'll just be one point, maybe there won't be any at all. It depends on what the graph is. Maybe there are loads. We'll see some examples. But wherever there's a change, where it's all of a sudden goes from being concave down to being concave up, or concave up to being concave down, that point there would be called a point of inflection. So clearly, in order to actually understand what this means, we need to know what concave down and concave up means. So it's, to begin with, here at the moment in Year 12, we can give a more precise definition in the second year of A-level. But for now, it's just based on what the graph looks like visually. So you're concave down if the bit of curve looks a bit like a frown, right? If it would form part of a sad face. So I'm actually going to try to be consistent with my colours here. So being sad, you feel blue. Being happy, well, I'm not sure you'd say you necessarily feel red, but we're going to use red for happy. Okay. So if we look at the next slide, this gives a little bit more information. So wherever a curve looks like part of a smile, even if it's not the full smile, that's called being concave up. And wherever the curve would be part of a sad face, a frown, it's concave down. So if you look at this bit of curve here, we've got the bit that's where you're happy. So if I can just draw on this, the bit where you're happy is this part here. And then there's more to say on this later, as I say in Year 13. But at that point there, something happens. And all of a sudden, it starts to be part of an upside down smile, a frown, right? At that point there, that is called a point of inflection. And so one way of remembering what concave up means is concave up is cup. Cup is this way. I suppose that really should be red, shouldn't it? Because we're saying red is happy. So there you go. And so I don't mean it needs to be the whole smile. For example, if I just draw this bit, there's something about that which it's not necessarily very easy to say exactly what it is, but there's something about that which is different to, for example, if I drew this instead. This is starting to sort of slope up and become a bit of a smile. This is, you know, part of what would have been a frown. So this part is concave up, and this part is concave down. And so if I just draw a wiggly line, right, if we ignore that last part, that bit looks a bit rubbish. Let's I've done the whole thing. Let's put it back. Let's see whereabouts we're happy and whereabouts we're sad. So we're happy kind of maybe from this point onwards, and then it starts to become sad. And the point is that there is an exact point where it actually starts. And we can be more precise, okay? It's not actually about being happy or sad, obviously, but this is a good way to try to learn it. So up here is kind of sad, and then something starts to happen at about here, where all of a sudden it becomes happy again. And then it doesn't stay happy, does it? It doesn't stay happy. What you need is to maybe go to about there, and then it changes. And then ignoring the fact that the rest of this is very unneat. I'm not sure why it deleted the red bit first. What you've got is a bit of happy there, a bit of concave up. Bit of concave up, and then we've got a bit of concave down. And then I'm going to ignore the rest of the curve there because it kind of goes bad. And then here, there's obviously a bit of concave down here as well. And so the idea is we've got a point here, a point here, a point here, a point here. All of these would be called points of inflection. And for the moment, that's all I need you to have in your head, okay? That is what a point of inflection is. It's where it goes from either being happy to being sad, or from being sad to being happy. And so I've got some actual examples, just two of them. So here is the graph of y equals sine x. So sine x is sad here, and then it starts being happy, and then it starts being sad, as in it's literally like a frown, and then it's a smiley face, like the mouth of a smiley face. So wherever it's red, it's concave up, and then wherever it's blue, it's concave down, because if you're feeling down, you're feeling blue. And each of these are points of inflection. And then one more example. So I've got some 1, 2, 3, 4, what looks to be a quartic. So this is like some x to the 4 plus blah, 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 blah graph. So all the way down here, it's part of a smiley face. And then something happens here where it begins to be sad, and then it starts to be happy again. And you can actually, in year 13, you'll be able to work these coordinates out. So it is something to do with differentiation. This is, it's all part of the same idea here. It's why I'm mentioning it as part of a differentiation topic. Now, I'm only mentioning this now because it helps to tell a more full story of the actual thing you need to know about, which is stationary points, and in particular turning points, which is actually the title of the you know, the part of the book that you're in. What did I say here? Section, that's right. The word was on the, I forgot the word there for a second. Anyway, so now we actually are going to start the actual lesson, right? So the words point of inflection are going to come up within this lesson. All you need to remember is it's where the curve goes from being happy to being sad, or from being sad to being happy. And there are actual words we use instead of happy and sad. If we're happy, we're concave up, and if we're sad, we're concave down. Right, so now this is the actual lesson. So the title is Stationary Points. You're going to have a few definitions that you're going to write down, and I'm going to talk you through them and give you some examples, and hopefully allow you to understand each of the definitions, okay? So you need to write the title, Stationary Points. You need to write definitions. You need to write what's on the screen, okay? So y equals f of x is some function. So if you want y equals f of x could be x squared, y equals f of x could be 3x to the power of 5 minus x to the power of 3 plus 2x squared minus 1. It's just some function, right? And in particular, we're in the differentiation chapter, so it's going to be something that you know how to differentiate. So it's going to be powers of x that are added up. And so the first definition is, well, definition 1, and it is actually what a stationary point is. So it's actually the title. So a stationary point of f of x is some point, so it's a coordinate that's on the graph. So this is a coordinate that's on the graph. Where when you work out the derivative at this point, where you work out the gradient at this point, okay, so there are two words that mean the same thing, you get 0. So it's any point where the gradient at that point is 0. So that's the definition. So let's first of all look at an example where we're just going to work out the stationary points of a particular function. Okay, so we've got this function here. Y is x cubed minus 3x squared minus 24x add 5. Now what I'm actually going to do is just very quickly show you what this looks like, because I think that would be quite useful. And that's what I would have done in class. I possibly should have planned this ahead and already had it, but you can't do everything right first time, I suppose, and you know, you make mistakes, you get better, don't you? So minus 24x plus 5, and then I'm going to take a little screenshot of it. Might want to actually rejig the x-axis. So maybe I want the x-axis to go from minus 20 to 20. Right, so this is what the graph looks like. I know you can't see it yet, but you're about to see it. So this is what the graph looks like, okay? So this is y equals x cubed minus 3x squared, take away 24x plus 5, right? That's what this graph looks like. And the question says, work out what are the stationary points. So we're going to, the answers, or the answer might just be one coordinate, it could be two coordinates, it could be many coordinates, but there's going to be some set of coordinates which for the x number satisfies f dashed of it is 0. So the gradient will be flat at that point, it will be flat. And if you actually have a look at the graph, that actually corresponds to something, you know, visually, graphically. If you look at, say you're on this, if you're here on the graph and you're trying to climb up it, right? It's quite steep, right? So it's very steep. Very steep. You're probably going to fall down unless you've got climbing equipment. And it's also positive because we're going uphill. So it's the point here is certainly not f dashed equals 0. Okay, it's f dashed. I mean, it's very steep. It's probably some quite big number that we could work out by, you know, differentiating this and plugging in what looks to be about x is minus 4.5. So we could do that. We're not going to. I've just noticed that I'm in the way, so let me just move me. Oh, that's moving that. Right, I'm now moved, so you can see what I've written. So whereabouts visually is the graph got gradient 0? Where would the flattest part be? Where would you like to stand to have a rest? So you might have a little think about that. But since this is a video and I can't question anyone, I'm just going to tell you the answer. The answer is, well, if you stood here, you're pretty happy, right? Because it's flat up there. The tangent line would be flat at the top there. And also, if you're down here, you're also pretty happy, right? Because it's flat down there. The tangent line at that point is a horizontal line. It has gradient equals 0. There and there. So we actually expect to have two coordinates. Now I'm also going to load up the calculator and make sure that you can see it. So do bear with me. Maybe one day I'll hire an editor, someone who can edit my videos for me, but for now you're just going to have to make do. So I've got the calculator, which we might need to plug the values in. Anyway, so how are we going to work out what these coordinates are? Well, they satisfy, so the coordinates here satisfy that we're looking for, which are of course called stationary points. They satisfy that the derivative at that point equals 0 for whatever the number is c. Okay, so you know, you could say f dashed of x, or I mean I could write f dashed of x. Maybe that's a bit easier. C would be the number itself in the answer. You know, if it turns out that f dashed of 4 is 0, then our c is 4. It's just a label. So don't worry too much about that. So this means we have to actually figure out what f dashed of x is, and then we're just going to set it equal to 0, and we're going to get an equation, and we're going to solve that equation and figure it out. So let's find what well, let's do y dashed. Let's differentiate. So I get 3x squared minus 6x, take away 24, and then 5 would differentiate and become nothing, right? Now, this equals 0 at a stationary point, and it's a really good idea for you to write in this little extra part, at a stationary point. Because the gradient doesn't just automatically equal 0. Okay, the gradient can equal lots of things, right? This is an entire quadratic function, right? This can equal a lot of different things. If we're on about being at a stationary point, we want to set this equal to 0. So if we were in class, I would say, okay, now solve this, right? It's just a quadratic, but since it's a video, I'm now going to solve this. So I'm going to divide everything by 3. That would be a good start. So x squared minus 2x minus 8 is 0. And then you'll notice that this factorizes as x minus 4, x plus 2 is 0. And therefore, there's a stationary point when x is 4. So that c would have been 4, or at minus 2. And if you actually look, well, here's minus 2, and here is indeed the you know, the stationary point, and here is 4. So I can't remember. I think I said I just made a random number up to see if it would be the 1, and actually it is, isn't it? And you could see that maybe. So if you go along to 4 and you go down, that's exactly where it is. Right, just here, right? So you've got a stationary point when x is minus 2. And remember what we did to figure that out? We actually solved an equation. We worked out dy by dx, and then set it equal to 0. And since that was then us solving a quadratic, well, we know how to do that, don't we? And because I designed it nicely, it gives you a nice answer. So what are the coordinates then? So you need to plug 4 back into this thing. And you also need to put it in -2 into it as well, right? Remember, if you want the coordinate, you're dealing with this thing, the actual original graph. Yeah, if you plug it into dy by dx, then of course you're going to get 0, right? So that's not the thing you want to plug it back into. So I'll use the calculator then and do. So we're going to do -2 cubed, take away 3 times -2 squared, take away 24 times -2, add 5. So that coordinate there, you might have been able to guess that it was about 33, but it turns out that it is exactly -2, 33. And then this coordinate here, we need to plug 4 in to our original y. So I'm just going to swap all the -2s with 4s. And I get all the way down at -75. And that actually looks, that's exactly -75 spot on if you look there. So that's pretty good. So 4, -75. So we've answered the original question then. So the stationary points are at -2, 33, and let's do that again, and 4, -75. That's right, isn't it? Remember those? Yeah. And so what this means is if you work out f dashed of -2, you get 0. And if you work out f dashed of 4, you get 0. And that means it is indeed a stationary point. Oh, and I can now, I'm just checking over there, and yes, the calculator's in the way, so let's get rid of the calculator. There you go. And I'll move myself back. There we are. Right. Okay, so apologies for the kind of, I don't know, haphazard approach to making this video, but it is what it is. I just want to do it all in one go. So that was the first definition of that's what a stationary point is. Fundamentally, that's it. It's wherever the derivative equals 0. So you differentiate, you get an expression for the derivative, you set that equal to 0, and you solve an equation. So, you know, that's absolutely fine. Now, what I might do is say, okay, do you want to try, you know, and then I would give you a question to try, but what's going to end up happening is you're just going to end up doing some practice out of the book anyway. So I'm just going to crack on with the definitions. If you have any questions or anything where you think I've gone too fast or you want me to explain something again, please will you send me an email and then tell me the timestamp. So what I mean is, you know, you might send an email that says, you know, hi sir, between 4:30 and 5:27, I didn't understand what you were on about. Do you think you could explain that part again? And then that's quite useful for me. What I would then do is I would obviously try to help you out. So please do feel free to get in touch and ask any questions. But I'm hoping I've made the definition of a stationary point quite clear to you, and that the example was useful. So that was only one of our definitions. I'm afraid there are a few more. Okay, so definition number 2. So now we know what stationary points are, so that where the derivative or gradient equals 0, they are either, there's two possibilities of what they could be. They could be turning points, which is what this section is called. Okay, so this section is called, you know, it's section 4.5, turning points. Or they could be what's called a stationary point of inflection. So just to very briefly touch on stationary point of inflection just before we actually, you know, move on with the actual content. Stationary point of inflection would mean that, for example, I'll just do a really easy example. For instance, in y equals x cubed, I'll just draw it like this. So there's my, it's not the best picture of y equals x cubed. In fact, a little bit later, in fact, I can do this now because it was something I was going to show you later, but I'll get to it again. Here's y equals x cubed. This part here is obviously concave down. Oh, and it's frozen again. Oh, it's fixed itself. Good. And then this part here is concave up. I mean, y equals x cubed is like the example for where someone has half a frown and half a smile, right? You've got half a frown and half a smile. Well, this here is clearly a point of inflection, right? This is a point of inflection. Now, if I work out what dy by dx is and set it equal to 0, because that would be a stationary point. So let's work out what are the stationary points of y equals x cubed. Right, this is tying in with obviously what we're doing. So if dy by dx has to equal 0, let's see what we get. Well, we get 3x squared equals 0, and therefore x squared equals 0, and therefore x equals 0. So x equals 0, and therefore, 0, 0 is a stationary point by the definition, right? It satisfies dy by dx equals 0. Well, what sort of stationary point is it? Well, it's a point of inflection is what it is, and because it's a stationary point, it's what's called a stationary point of inflection. Okay. Now what I'm going to do is I'm actually going to rub all of this out because I'm actually going to come back to it later. But that's what that's what a stationary point of inflection would be. Okay. Now it doesn't just happen with y equals x cubed. Okay. There's like lots of examples, but it's possibly the easiest example for that sort of thing. So if we go back to the definition up here, as I was saying, stationary points are either turning points, which is what we're actually going to really be talking about. I mean, where are we? I mean, we're nearly half an hour in, but we're finally going to actually begin what we're talking about. Remember, it would have been the equivalent of a double lesson, so don't you worry about it. We will get there eventually. Stationary point or stationary point of inflection. So that is where. So this second option would be an example like this. Okay, it's like the example. If y is x cubed and you do y dashed equals 0 gives you 3x squared is 0, gives you x is 0. You have got a stationary point there, but it's not a turning point. It is a point of inflection. So it's called it's given the full name, a stationary point of inflection. If you have a look at the previous examples of points of inflection that I showed you up here, can you see that the gradient here and here and here and here, the gradients there aren't 0. They're definitely not flat there, are they? And they're not flat here either. So these are points of inflection, but they are not stationary points of inflection. So you can have stationary points of inflection and you can have non-stationary points of inflection. And when you have a stationary point, you could either have a turning point or it could be one of these funny things, these stationary points of inflection. Right, I think you should really, really make sure you understand everything up until this point. What might help you is the following slide. We have got a little Venn diagram of the possibilities, right? You're a stationary point automatically if you satisfy f dashed is 0. So if you satisfy that the gradient is 0. Now, you could be a point of inflection, and in which case you're in the middle here, right? You could be a point of inflection. If you are, and you're a stationary point, then you're what's called a stationary point of inflection. So it's kind of like, it's the intersection of both of these. It's got to be stationary and it's got to be a point of inflection. This is what the chapter is about, and what we'll finally get on to talking about on the next slide. Now just over half an hour in. Or there's these things, non-stationary points of inflection, which you've already seen some of, right? These are examples of non-stationary points of inflection, okay? A point of inflection is just where it goes from being happy to sad or sad to happy. Now that can happen at any gradient. That can happen at any gradient. Doesn't have to be at 0. So, you might like to make a little copy of this Venn diagram. This here is what we're actually doing. That's what we're actually doing. And in particular, it's when f dash of c is 0. Now, f dash of c being 0 doesn't guarantee a turning point, because you could have one of these, right? F dash equaling 0 doesn't guarantee being a turning point. Okay? Remember, f dashed being 0 is what it means to be a stationary point. And stationary points are either turning points or stationary points of inflection. Right. So, you imagine the situation. You have got a stationary point, and it so happens that it is a turning point. So we'll see in a second how we're going to be able to tell. To begin with, we can just think about it visually. So turning points are either a maximum or a minimum. A maximum is a top of a hill, and a minimum is the bottom of a valley. So let's go back to this picture up here. This point up here is the top of a hill. This point down here is the bottom of a valley. This point here is called a maximum, and this point here is called a minimum. So it's at this point that if you went to page 106 in your book, you would see two little pictures that look just like the top of a hill or the bottom of a valley. Now, if I go back to what it says here, a maximum is the top of a hill, and what happens there, the gradient goes from positive to negative. Let's have a look at what I mean. I mean, when you're at the top of a hill, the gradient was positive, 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 positive. Oh, it's starting to get more and more sort of flatter and flatter. Oh, the gradient's now 0. Oh, now we're going downhill. The gradient is negative, 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 negative. It went from, and so this, I might copy and paste so we actually can look at this again without all the writing on it. So here we have a positive gradient on this side. Here it is exactly 0. And then we have a negative gradient on this side. So if it goes from positive to negative, it's a maximum. That's what I said there. It's a maximum if it goes from positive to negative. And down here, well, it's certainly a negative gradient because you're tumbling downhill. You're falling down. It's a negative gradient. Right at the bottom, you've got a 0 gradient, and then it switches around and becomes positive again. And so if that happens, it's a minimum. So you've got maximums and you've got minimums, or maxima and minima. So again, you probably just you should have a nice ordered list of definitions, and then you want to really sort of focus on them, make sure you understand them, tie them in with any pictures that you can. I've drawn a picture here for you. It's a maximum, it's the top of a hill. It goes from a positive gradient to a negative gradient. So it's like you're climbing, that's positive, then you fall down. It's negative, that would be the top of a hill. You climbed the hill, then you fell down. And then at the bottom here, you fell down, you've reached the bottom, and now you're going to go back up. So it's gone from negative to positive. That was the bottom of a valley. So, how could we tell that these were going to be turning points? Remember, it was very easy to find out that they were stationary points. Let me go back to the Venn diagram. Stationary point is just differentiate, set it equal to 0, and work out what values make it equal 0. So you're solving a little equation. How can you then tell, without looking at the graph, that you've got a turning point? And then more precisely, imagine you now know it's a turning point. How do you know it's a minimum? Or how do you know it's a maximum? Well, we do have the option of drawing it and looking, right? We could do that, but it could be more complicated, and it could also ask you to do it without drawing the graph or without relying on a graphical approach. So this is where definition number 7 comes in. The nature of a stationary point can be determined by finding the second derivative. Okay, so this is where you have some y, you find dy by dx, and then you differentiate that again, and you get what's called the second derivative. Okay, so you might have f of x, f dashed of x, and f double dashed of x. Now, this is your second derivative, so you just take what your first derivative. Oh, I've written something where I am. Let me just move this away, actually, and then move me back. There we go. There I go. And so that's your second derivative, and basically, if you remember, a stationary point can either be a turning point or a stationary point of inflection. Now, unfortunately, it's not going to be possible to use this test to instantly show that you've got a stationary point of inflection. However, the test will tell you whether or not you have a minimum or a maximum. So how does the test work? Well, that would certainly be a good thing to now tell you. By the way, the only reason this might seem rushed is because there is literally no feedback. I am just giving a full explanation. So any questions you can think of, anything that you want to rewatch, anything you want to pause, make notes, look up, you can do this. Okay, this is the full explanation with as much of what I think is necessary as possible. There's probably things I'll have missed or things I haven't explained as well as I should. But if anything like that does come up, please do just send me an email. So how does the second derivative test work? How are we going to work out, once we've got our coordinates that are stationary points, how do we now work out what sort of stationary points we have? So that's what this is about. So suppose we have a stationary point. For example, imagine it was the minus 233, but we didn't have the picture. So suppose we've got a stationary point. Well, what you do is you work out the second derivative and you plug the x coordinate into the second derivative. If that comes out as negative, then you've got a maximum. So that seems a little bit backwards, but it is the way round, I'm afraid. If the second derivative is negative, you've got a maximum. So we might as well try that out with our question from above. Let's work out what the second derivative is. So I'm just going to look here to here's my y dash, right? So let's work out the second derivative. So the second derivative is 6x minus 6, right? So now let's put y dash of minus 2 in. So I've got 6 times minus 2, and then I'm taking away 6. So that's minus 12, take away 6 is minus 18. That's negative, so it is indeed a maximum. And we saw that it was a maximum, wasn't it? All right, and then back to this. Okay, it turns out that if you do this and then you get something positive, then it's a minimum. So it seems a little bit backwards, but as I say, that is the way round. So let's try that out with putting 4 into the second derivative from our question from before. So if I do y double dash of 4, I get 6 times 4, take away 6, which is 18. Well, that's a minimum then, because that's positive, and indeed it is a minimum. So if it's negative, then it's a maximum. So this is really important, and this is what you're going to be using to help answer questions in exercise 4.5a and exercise 4.5b. Now, this is really, really important. Really important. Now, you to begin with, you're actually only going to get questions where it's either less than 0 or greater than 0. That's how it's going to be at the moment. But for the full story, I'm going to also, as part of this, explain. And maybe if I was teaching this lesson, and I could judge how it was going, I might decide, well, actually, I might just not bother mentioning this. However, it is part of the full story and something you'll need to know for the full A level. And since it fits here into one neat kind of package, it's worth me including. So if you do this test and you actually get 0, so not negative, because if it was negative, it would be a maximum. And not positive, because if it was positive, it would be a minimum. If you actually plug in your value to the second derivative and you actually get 0, then the test is inconclusive. So what that means is it could be anything. It could be a maximum, could be a minimum, could be a point of inflection, might not be any of those, could just be like, well, if we think about it, if we're only applying this test because we've got a stationary point, it's going to either be a maximum or a minimum or a stationary point of inflection. However, the point is we can't actually tell what it's going to be. Okay, that's the point. If f double dash or d2y by dx squared, if at that point you get 0, there is no way of telling what sort of stationary point it is. And I'm actually going to illustrate some examples that actually, where on the one hand it could be this, or on the other hand it could be something else. Okay, so hopefully that will illustrate why. But it's really important that you remember that for the second derivative test, if you get 0, you can't tell. It could be a maximum or a minimum or a point of inflection. You have no way of knowing. More investigation would be necessary. So, you might draw it, but you can't rely on the second derivative test alone. However, if you do get a negative answer, then you know it's a maximum. And if you get a positive answer, then you know it's a minimum. Okay, now this is where you might want to box this off and just say, look, this is kind of extra now. This is just kind of delving into a little bit more detail about the second derivative being 0. Okay, so point number 8, if you have a point of inflection, any kind of point of inflection, whether it's stationary or non-stationary, then at that point, the second derivative will be 0. However, not all points that have second derivative 0 are going to be points of inflection. Okay, this is one way. This is a one-way implication. If you have a point of inflection, then the second derivative is 0. The other way around, not necessarily. If you have a second derivative equals 0, could be anything. Doesn't have to be a point of inflection. Okay, so it is very much point of inflection. Then you have f double dash is 0, but the other way around is not true. Okay, it could be anything. And I'm going to show you some examples in a moment where you have second derivative equals 0, but you do not have a point of inflection. So this is a bit like, for example, if you're a square, then you're a rectangle, okay? Because a square is a special type of rectangle. But if you're a rectangle, then you're not necessarily a square, right? It's like saying all squares are rectangles, but not all rectangles are squares. All points of inflection have second derivative 0, but not all points with second derivative 0 are points of inflection. So this is just what I was saying there. The converse is not always true. If you just are given some random point where the second derivative is 0, that's not enough to draw any conclusion. And to see why, we're going to consider these 3 examples. Okay, so y is x cubed, y is x to the 4, and y is x to the 4 minus x. So let's, and we're going to choose the point x is 0 for all of them. Okay, so the first one is y equals x cubed. So y dash is 3x squared, and y double dash is 6x. And if you set this equals to 0, and it's actually what we had before, x was 0 is a stationary point. So it's flat here, perfectly flat. And also y double dash of 0 is 6 times 0 is 0. So this is an inconclusive second derivative test, okay? We don't know. It could be a maximum, it could be a minimum, it could be a point of inflection. By actually looking at the graph, we can see that, oh, actually, yes, by inspection, it's a point of inflection. This alone, this fact alone says, or rather maybe tells us nothing. Okay, and to see what it doesn't tell us what it's going to be. It doesn't tell us that it's going to be a point of inflection. Okay, let's see what happens if y equals x to the power of 4. So I'm going to repeat the same idea. We're going to get slightly different derivatives, obviously, but we're going to see something different. Okay, so here's y equals x to the 4. So y is x to the 4. If I differentiate it, I get 4x cubed. And if I set that equal to 0, you can see that x is 0 will be a stationary point. Because, well, if you put x is 0 into here, you get 0 equals 0, so that's what you want. And of course, down there, you do indeed have a stationary point. It's flat down there. It looks flat at lots of places along there, but I assure you it's only perfectly flat at x is 0, just because of the scale you're looking at it. And, well, what sort of point is that? I mean, is that a point of inflection? I mean, that's a minimum. That's very much definitely a minimum. That's the least x to the power of 4 can be, is 0. Anywhere else, and you're going to have something greater than 0. So this is definitely a minimum. Yeah, definitely a minimum. And again, that's by inspection. However, watch this. If I do the second derivative, I get 12x squared. And if I do the second derivative of this sort of point here, so we're trying to categorize this point, so we're using the second derivative test. If I do y double dash of 0, I'll have 12 times 0 squared, which is nothing. So I got 0, so I don't know what sort of point it is. It doesn't tell me anything. It doesn't tell me that it's going to be a minimum, just like this didn't tell me it was going to be a point of inflection. Y double dash equaling 0 could be a point of inflection. Y double dash being 0 could be a minimum. And I could also, obviously I could have, a very simple example to show it could also be a maximum would be to just do y equals minus and then x to the 4, and it would just flip upside down, then you'd have a maximum. So the second derivative test, if you get 0, you cannot tell. Watch what happens with this one. So this is the graph y equals x to the 4 minus x. So let's do y is x to the 4 minus x. Let's do y dash, which is 4x cubed minus 1. And then y double dashed, which is 12x squared. Now, you can see this point here is where the minimum is. So this would be found by setting the first derivative equal to 0. So you'd have x cubed is a quarter, and then x is 1 over the cube root of 4, so some horrible number, right? Now, if I plug that into here, I'm going to get something positive, so it is indeed a minimum. So this point is absolutely fine for categorizing using the second derivative test. So if I plug that in there, I'm going to get, well, it's going to be a positive number. I've got some number, I'm squaring it and timesing it by 12, it's going to be positive. And since the second derivative is positive, it's a minimum. So that's fine. But if you notice, if you do y double dash of 0, where you get 12 times 0 squared, which is 0, y double dash of 0 being 0, there's nothing special about it by itself. Y double dash of 0, well, it doesn't tell me anything. It's just it's going downhill there. It's not flat, it's not a point of inflection, it's not a minimum, it's not a maximum. Y double dash being 0 is not enough on its own. And that's really important to try to remember, okay? So I'm going to just bring this slide back. So to recap, you get a stationary point by differentiating and setting equal to 0. You work out which points that works for by solving the equation. For each of those, you're going to use the second derivative test. So you differentiate again to get the second derivative. You plug those stationary point values in, those x's. If any of them come out as being negative for the second derivative of them, you've got a maximum. If the second derivative of those points at those points is positive, you've got a minimum. If the second derivative is 0, you cannot tell anything. It could be anything. Okay, it could be a minimum or a maximum or a point of inflection. Okay, but if you were to compare that to f dashed of 0 of something equaling 0 is enough info to get something interesting. Okay, it means you've got a stationary point, right? So it's it's quite useful to differentiate and set equal to 0, okay? Because you get where it's flat, and that's possibly where you have a maximum or a minimum. And of course, you can work those out by either looking with your eyes or by using the second derivative test. So there's kind of like a little upgraded version of this Venn diagram. So you've got stationary points where f dash to c is 0. So the first derivative equals 0. Now what I'll say is you can have minimums where you weren't able to use the second derivative test to establish that. Like, literally this being an example. This is still a minimum, but we didn't work that out using the second derivative test. The second derivative test is kind of like, hopefully this is going to work. Hopefully I'm going to get something positive or negative, right? But if it gives you something that's 0, which it does, it's like, oh dear, I'm going to have to do something else then. Maybe I'll draw it or, something like that. So yeah, you could also be a stationary point of inflection, of course. Now this circle here is what points of inflection are, which remember is actually nothing really to do with what we're talking about in general here about stationary points and turning points and things like that. So your points of inflection, remember, are just where the graph goes from happy to sad or sad to happy, right? Or which is what concave up to concave down or concave down to concave up. And then I've got this little box here with some information in. So all points of inflection will have second derivative equals 0. Okay, that's just a property that they have. But not all points with second derivative equals 0 are points of inflection. Okay, we saw one here. There's a point there with second derivative equals 0, but it's not a point of inflection. Here's a point here with second derivative equals 0, but it's not a point of inflection. What this is saying is, if I go all the way back here, at this point here, the second derivative will equal 0. At this point here, the second derivative will equal 0. At all of these points, you're going to have second derivative equals 0 because they're all points of inflection. And then this is final sentence here. If f double dash is 0, then unfortunately the second derivative test is inconclusive. Basically, the second derivative test fails and you'd need to do something else. Now, thankfully, because you're in year 12, the second derivative test won't fail for your questions. You just need to remember if you get something negative, then it's a maximum, and if you get something positive, then it's a minimum. And then I thought what I would try to do is, if I make those blank, I can fill in the possibilities. So we can have a maximum. So this is a maximum. Or we can have a minimum. Right, and it's like literally the point at the top or the point at the bottom. Or we could have what's called a stationary point of inflection. So the best example is like y equals x cubed. So at that point, it goes from being sad to being happy, but the gradient also happens to be flat there. So that's flat. And then the last one is these non-stationary points of inflection. So all I need to do is just basically do anything else where it's not flat. So it goes from being sad to being happy. So that happens at about there, although that's not a particularly good example. Let me try again. So about here, right? It goes from being happy to being sad, and that definitely does not have a flat gradient. Okay, so that there is a non-stationary point of inflection, right? It goes from being happy down here to being sad up here. Okay, so those are your options, right? And really that's the entire that's all of it in a nutshell. That there is nothing more to say. There is only the stuff in year 13 where we go into a bit more detail with points of inflection. Okay, so I'm just going to kind of finish with a second example about determining the natures of the stationary points of the function. Now, here's actually something I've just realized, of course. I've already answered this question, haven't I? So this was the same question, but the determining the natures part I've also already done that. If you remember, if I go all the way back to here, we determined the nature of this one here, this minus 233. We determined that it was a maximum. Because when you do the second derivative of that point, you get a negative. And we also did it for 4 minus 75. If you plug 4 in, you get 18, and that's positive, so it's a minimum. So actually, I've already done that, so there's not really anything else to say. So that literally the next slide, now just over 1 hour. So you can tell how with like pauses and with questions and stuff like that, and then a bit of practice time, this is ideally going to fill either 2 or 3 lessons depending on how much extra time is needed. Obviously, as a single video, it's been about an hour, which it really isn't that bad actually. So yeah, here's the last slide. So the question's on page 108 of your textbook. So I've written the key points up again. So this is really the absolute fundamentals. So a stationary point is one where you've got the first derivative equals 0. So you work out the first derivative and then set it equals 0 and then work it out. And then to determine its nature, so that's whether or not it's a maximum or a minimum, because remember, it's either going to come out as being a maximum or a minimum, or the second derivative test is going to fail, right? You can't, if it comes out as being 0, right, this bit here, it's inconclusive, right? It could still be a maximum or a minimum. It's just you can't tell using the second derivative test. So yeah, if the second derivative test, if it's negative, you've got a maximum there, which is the top of a hill. And if the second derivative is positive, then it's a minimum, so that's the bottom of a valley. So this is like, you know, where it's gone like this or where it's gone like this. Okay. And sometimes the question will say use your inspection. So that is like literally you using your eyes to see if it's a maximum or a minimum. So what I might do then is say, look, you would now do some practice. You can end the video, but what I'm going to do is I'm going to go through 1A. So within this video, I'll go through 1A, and let's have a look. And okay, so then number 2. I'll go through 1A and the whole of number 2. Okay, and then maybe in future videos I can go through more questions. Some people might ask me questions and I'll go through them. That's what we'll do. So here's what's actually going to happen. I'm going to delete, or rather I guess crop this, and answer these questions at the side here. So you might want to pause and make those notes before they go forever. Whoops, didn't mean to delete the whole thing. There we go. Right, so 1A. So we've got y is x squared plus 4x minus 5. And it says for each curve, work out the coordinates of the stationary points. Right, so we're going to do dy by dx has to be 0 for a stationary point. So dy by dx is 2x plus 4. So I need 2x plus 4 equals 0, which gives 2x is minus 4, which gives x is minus 2. So at x is minus 2, we have a stationary point, and it says to do it with inspection. So I'm just wondering, is there, I think if you look, this factorizes as x minus 1, x plus 5. 5 times minus 1 is minus 5, 5x minus x. So we know it goes through 1 and minus 5. And then here at minus 2, there's going to be a stationary point. So it looks like this. Very hard to draw with this bit of equipment I've got, but there you go. This is the graph of y, and clearly it's a maximum. I got through the whole video without really making a mistake, and I save it right for the end. So if you heard me say maximum there, you've watched the whole video. Well done. Clearly I meant to say minimum. So what time? We're 1 hour and 5 minutes. Okay, no, clearly. So apologies for that. It's clearly a minimum. Sorry about that. I'm just so excited for the video nearly to be over. So we're at the bottom of a hill, aren't we? So it's a minimum. It also corresponds directly to what would happen back at GCSE when you'd be asked to find the vertex of a graph. So you'd only be asked that for quadratics, and it would involve completing the square and finding the minimum point of a quadratic, or if it was a minus quadratic, you know, a flipped one, a sad quadratic, the maximum. So it actually turns out this is a much faster way of finding the vertex of such a graph. Okay, so at -2, and then what do we have to do? So 4 take away 8 is -4, take away 5 is -9. So -2 minus 9 is a, let's get it right this time, minimum. Okay. And so this is actually what's called the vertex of this graph. You might remember that from GCSE, but don't worry too much if not. So that was that. So what else did I say? We're going to do question 2. Okay. So number 2. We've got y is x cubed minus 6x squared. So I'm going to need to do dy by dx because it's asking me about turning points. It tells me it's got turning points. So turning points are just a special case of a stationary point. So I'm definitely going to have to do dy by dx equals 0 for a stationary point. And, you know, in particular for a turning point, right? Because a turning point is a type of stationary point. Let me take it all the way back to this slide here, right? A turning point is a type of stationary point, and you can either be a maximum or a minimum if you're a turning point. So we have 3x squared minus 12x, which by the way is 3x brackets x take 4. This has to equal 0. So x either equals 0 or x equals 4. So the stationary points are 0, 0. Okay, so I'm going to put 0 in there. And 4, so 4 cubed is 64. Do I want to use a calculator? Yes, I think I probably do. Just going to use it quickly. So 64, take away 6 times 16, and 4 minus 32. So I think that's right. 4, I'm just going to double check because I really don't want to make another silly mistake. 4 take away 6 times 4 squared. Yeah, minus 32. So we've got, these are stationary points. And this is where actually, I don't like that the book tells you right away that these are turning points. It's like we have to work that out now for ourselves. We just know that they are stationary points. Okay, and cubics can have points of inflection in them, right? You know, y equals x cubed being the, you know, the main contender for that. So there's no guarantee that you have turning points. The book is just kind of giving the game away and telling you that these are indeed turning points, but it's kind of irrelevant. It's like it could call them a stationary point and still ask you to determine their nature. So we need D2, so this I guess was work out the coordinates. So we've got, well, there's A, and then we've got B, and I was going to write d2y by dx squared, which equals, where is it, 6x minus 12. So I'm going to do, for the first one, so this is for 0, 0, I have 6 times 0 take away 12, which is minus 12, is a maximum because it's negative. And for 4 minus 32, I have 6 times 4, take away 12. 6 4s is 24, take off 12 is 12. So that's a min. That's a minimum because it's positive. Okay, so this was the second derivative of 0 and the second derivative of 4. When I use 0, I got a negative, so it's a maximum. And when I put in 4, I got 12, which is positive, so it's a minimum. So these are stationary points. So actually, in particular, right, 0, 0 is a max, is a maximum, and 4 minus 32 is a minimum. Right, and then what's the last question say? Oh, sketch it. Okay, let's see if I can just fit that here. So we know it goes through 0, 0, and in fact we can factorize this, can't we? We can write x squared. In fact, what am I doing? That's x squared, x minus 6, which means it crosses the x-axis in two places, at 0 and at 6. So it's only going to cross there and there. At 4, it's got a minimum. And at 0, 0, we have got a maximum. So what it does is it comes up like that. Then there's a maximum there, so it has to start coming down. Then there's a minimum there and has to start coming back up, and then it actually, well, if I move that along slightly, then it'll go up and go up like that. Okay, so not the best of, and in fact my face is literally blocking it. Let me delete this. Let me delete what I just drew. Let me whoop. There you go. My apologies. Right. Delete that. Move this along. Right, and now I'll talk in a bit more detail about what I just did there. Again, if you know, if my living was to make YouTube videos, I would obviously edit these, but you know, never mind. So I'm just going to draw a quick set of axes. Now, what I did before was I said that y could actually be written as x squared x minus 6. And so the question is when can this equal 0? So that's going to give us the coordinates where it crosses the x-axis. So this happens when x is 0 or when x is 6. So we only have two intersections with the x-axis. There's one there and there's one here, right? So that's 0 and that's 6. And we also know that at 4, so here I've got 4, I guess there's 0, there's 6. At 4, all the way down here at minus 32, I've got a minimum, right? I've got a minimum. So it kind of goes like that, and then it'll start coming back up. So that's the bottom of a valley. So I have to draw in the bottom of a valley. Like, I don't have any choice. And then 0, 0 was a max. Was a maximum, so that's the top of a hill. So I actually have to draw the top of a hill. Like, it must be going up, and then it gets there, and then it has to start coming back down again. Well, this is now actually enough information to draw the whole graph. It's going to come up like this, right? It hasn't started up here, because if it did, it would have to turn, and we don't have any other turning points. Also, some basic GCSE knowledge is about what the shape of a positive cubic is. So it'll start off like down here, negative, then kind of do a little swoosh, and then go back up being positive. Okay, so this is the general shape of a positive cubic. So here's the little swooshy part. It's coming down again, and then it goes back up again. And there you go. Now, if I'm going to see how close I was, so I'm actually going to type this into Desmos, and we'll see what it actually looks like. So I'll take a little screenshot and let's see. So that's actually what it looked like. Now, how close was I? Well, I mean, the overall shape is right. It's coming up. I mean, obviously this is neater. Then there's this maximum that we found and this minimum at, if you look at the scale, yeah, that's about -32. And then it starts going up, and here it crosses at 6. And then up it goes. Okay, so the sort of tools that this is used for is, what on earth? Where did that come from? Right, there you go. I'm not sure what happened there. So the sort of thing this is going to be used for is for like more advanced curve sketching. But anyway, hopefully this video has been useful. I'm sorry if parts of it felt rushed. I'm sorry if at times parts felt quite complicated. I would just urge you to just watch key parts again. Make sure your notes are in a nice, neat, kind of organized structure, and ask me any questions in an email. Okay, see you later. Bye.